Hi, welcome. To this video, we're going to continue our discussion of LES filtering. So previously, we talked about simple box distribution, box averaging. Remember that G of R is some sort of weighting function, where if we wanted to take a spatial average of a velocity field, we don't have to always take a simple average. Let's say this cell has this velocity, this cell has this velocity, this cell has yet another velocity. Then the average is to, the average is just to, what do you call that? Add them all up, integrate them, and just divide through. That's the general way of thinking. Okay, but not necessary to do that. We can actually give, for example, we can give velocities closer to the point of interest. Let's say x1 over here, I was talking about that. We can give velocities closer to the point of interest more weight. So let's say you have G of R, you have this this alternate shape called Gaussian. It's a Gaussian distribution. So that's where we have this G of R come into play. Okay. So so far, if we want to use this averaging method, this weighting factor G of R, so the way of getting our filtered velocity, okay, U bar x of t will be equal to the integral of G of R and U x minus R t dr. Okay, so this average, this integral will give you some sort of average, right? Because this is some sort of a weighting function, and integral is like summing up the product, right? Summing up all of these with respect to R. So I'm summing up G of R times the velocity. So yeah, this integral is basically, I'm taking a weighted average of every single velocity over the whole domain. All right, because R ranges from 0 to infinity. So that's how I do my averaging. So if you have a Gaussian distribution, I'm not limited to a box here. I can sample every single velocity in the whole domain, except that velocities here are given more weight than, let's say, a velocity here. So it's sort of a weighted average. So G of R gives you a weighted average function when it comes to integrating. But you may notice one more thing. Okay, G is also in general dependent on x, right? G is in general dependent on x. So what does this mean? It means that, okay, I don't fix my weighting function to be uniform across this whole thing. Meaning to say, over here, I can use, hypothetically, I can use a box, and let's say over here, I want to use a bell curve. Or let's say over here, I want to use a smaller box. So you see, these weighting functions at different points in x, G of R will change. So if I want to change, G of R with x, and G of R is this weighting function I'm talking about. This is a weighting function with respect to x. I can do so simply by making G of R a function of x. Okay, so U x t equals to integral, okay, integral of G of R x into U x minus R t dx. Okay, so apologies for the messy writing, but yeah, that's more or less how we get our filtering done. Of course, if I write the equation nicely in word editor, it will look something like this, and you can paste it here. Okay, never mind. I will use snipping tool then. Okay. So that's the final equation that you see inside the LES model. That's what it kind of looks like. So whenever you see this, just remember it's an average process, and G is just some sort of weighting function where I say, okay, I want to weight my velocities differently at different points of interest in the fluid, and this is what this equation is trying to say. Okay, so hopefully that clarifies, you know, what this filtering process is trying to do. Now, of course, the clever bit of LES is to check what this G is, because there are many models, just like there are many Reynolds average, Navier-Stokes models, many ways of modeling, many ways of averaging. Likewise for this LES way, there are different weighting factors you can use to put this G of R. You can use a simple box method, you can use Gaussian, you can use any sort of function you want. It's just a matter of which actually works best. Okay? So what shapes can G of R take? There are some actually given in this book called Turbulent Flows. One of them is box, the other one is called Gaussian, and then you have sharp spectral kind of a shape, and then you can of course have a Cauchy shape as well. Of course, box and Gaussian are the easiest to understand conceptually. All right, so the box function. All right, you see this thing called box function. So you can discuss what that box function looks like. Oh man, this is so messy. All right, let's see. Oh, this looks very beautiful actually from a distance also. Okay, never mind. So the box function. The box function is like this. We have G of R, and this is independent of X. Okay, so I just write G of R, not G of R and X. G of R equals 1 over delta times H into half delta minus R, the modulus of R. So what is this saying? Okay, if I make this is actually some sort of the box width. Right, this is some sort of a box width, right? So what would the box width look like? So if we have G of R versus R, I will have some finite box width. I will call it delta. So this is the length scale of the box. So G of R versus R is as such. Okay, so and then this, what is this H? This H is likely the Heaviside function. So Heaviside function is such that it is 1. Okay, it is 1 at yeah. So what is the Heaviside function? The Heaviside function, okay, it is equals to 1, where x is greater or equal to 0, and is 0. Okay, excuse me. Sorry about that. It is 0 for, let's say you have an x less than 0. So where is x equals to, let's say 1? Okay, I mean, where is this x greater than 0? So you have this function half delta. Half delta, it is the, I mean, that's half the length of the box. So I should of course draw it such that it's delta is like that, where it's evenly spaced in the center. We should draw that box such that it is half delta this way, half delta the other way, right? So yeah, it's half delta on the left, half delta on the right. So the fact is that if I increase my distance, because this is a modulus, if I increase my distance more than half, let's say I have r over here, so r is more than half delta, okay? Or let me type even better. So you have modulus of r more than half times delta. This Heaviside function is less, this value inside becomes less than 0, so that this Heaviside function should give you 0. So it is one where the box, I mean it is within the box width. If r is less than half delta, this box width, then we will have a value of 1 for this Heaviside function. Otherwise, if r is greater than half the box width, which is in outside here, it will be 0. So let's say it could be over here as well. And over here, you have the modulus of r less than half delta. Okay, so you have modulus of r, mod of r less than half times delta. Okay, so this is what the box function is like. Now, of course, you cannot have it one all the way around. You have to make sure that the area under this curve, or area under the box, so to speak, it is equals to 1. So to do that, you need to so-called set this Heaviside function, half integrate, all right, half delta minus r. Okay, you need to set it equals to 1, so you have to multiply it by some constant, and these limits of this integral are from minus infinity to infinity, and it just so happens that this c, this constant, equals to delta, because if you take this integral, you multiply I mean the height, which is 1, the height is 1, and then the length is actually delta, which is the box size. You integrate this function from 0 to minus infinity to infinity, you will just get 1 times delta. All right, half delta minus r equals to delta. So if you want to make this whole thing 1, you need to have it such that 1 over delta. Okay, the other way of writing it is integral from minus infinity to infinity, 1 over delta, multiply into the Heaviside function, h of half delta minus mod of r dr. Okay, I should write a dr here, and here as well. And I should multiply, I mean if I do this, this will be equals to 1. Therefore, this can be my g of r. So that's generally how the g of r works, at least for the most simple box functions. And of course, the trick is how will you determine this box size? And of course, if you see in this expressions, delta doesn't just appear in the box function, it can appear in many other functions as well, such as the Gaussian function. So the question becomes, how do we determine this delta, this characteristic length? So delta is some characteristic length. Okay, how do we actually deal with this characteristic length. We'll talk more about it probably in the next video, and we'll continue talking more about LES models. Thanks for watching with me. Please leave a like and subscribe if you found this helpful or interesting. Hope you learned something useful. Okay, see you again.